Hi there, and welcome to Raylene Math. In this first video on series, we'll take a look at the prerequisite knowledge that we need to go forward into finite and infinite series, arithmetic, geometric, telescoping series, as well as moving into power series, Taylor series, and MacLaurin series. To start then, we want to see how to express rational numbers as repeated decimals, ratios of integers, etc. The first question asks, does 0.9 repeating equal to 1? But before we take a look at that, let's look at the process to convert a repeated decimal into a ratio of integers, a rational number. There's the word ratio here and the word ratio here. So the first thing we will do is to let x equal the repeated decimal. And this is an interesting one because the repeat doesn't begin immediately after the decimal place. So the first thing we're going to do is telescope this by multiplying both sides of the equation by 100, which will isolate the repeated part of the decimal after the decimal point. And then ideally, when we're telescoping, we want to subtract something so that all of the infinite parts disappear. So if we multiply by another 100, we will still have a 0.25 after the decimal point because this 0.25 is really repeating again. So we have another 100 multiplied by this, so we get 10,000x is equal to 3,625.25. And now if we subtract the first equation, well rather the second equation of 100x from here, making sure that we have the repeated part, on the left-hand side we're going to get 9,900. And on the right-hand side, the 0.25 repeating part will disappear, and 3,625 subtract 36 is going to be 3,589. And so we can express x, which is the same x as the beginning, as a ratio of two integers, 3,589 divided by 9,900. And so if we were to approximate that in a computer program, a calculator, we can see that 3,589 divided by 9,900 doesn't reduce, and so if we approximate it as a decimal, we get 0.362525, which is just calculator speak for the repeating decimal. So, going back then to take a look at the first question, does 0.9 repeating equal to 1? We may have a sense that they can't possibly, because 1 minus 0.9 repeating does not equal to 0. And there's this sense that eventually, after we stop subtracting, there's going to be a 0.1 at the end. But the whole idea of this repeating is the sense that we have an infinite sequence, if you will. We could say that 0.9 repeating is really made up of a sequence of numbers, or a series, 0.9 plus 0.9 plus 0.009 plus 0.0009, and that sequence goes on forever. And it turns out that we're multiplying by a constant or a common ratio here of 1/10 every time. And when we do something like this, we're getting what's known as a geometric series, or at least the terms, without adding them together, form a geometric sequence. But when we add the terms of the geometric sequence together, we get the series. So the question is, does this equal to 1 or not? In other words, does this geometric series converge? Well, before we get too deep into that question, we can just take a look at writing 0.9 repeating as a ratio of integers. And so to do this, we use the same let statement. We let x equal to 0.9 repeating, and therefore 10x is equal to 9.9 repeating. And if we subtract the second one minus the first one, we get 9x is equal to 9 minus 0, which is 9. And sure enough, x is equal to 9 over 9, or 1. And therefore, the answer is yes, 0.9 repeating does equal to 1. Now, this might seem out of place, but just to kind of get us used to making some patterns, we have to have some number facts down. And one of the set of number facts that is very helpful is the perfect powers of 2, 3, 4, etc. So just to kind of get an idea of this, we also want to reiterate some notation, namely that the 2 is the base, and the 1 is the exponent, and the output is the power. And so the first 5 perfect powers of 2 are 2, 4, 8, 16, and 32. And so here we really want to make sure that we are calling the to the base, the number up here, the index, is the exponent, and the output number is the power. The next question is to solve an absolute value inequality, which doesn't seem connected, but it will be once we get into power series in looking at the interval of convergence. This is asking us to represent the solution graphically in 1 dimension and 2 dimension. My favorite way of doing this is graphically, and the absolute value means the distance, and the left-hand side says the distance between, as indicated by the subtraction, x and 3. That distance is to be greater than or equal to 5. So we're really asked to find the x values such that the distance between x and 3 is equal to or more than 5 spaces. In other words, we want the distance between, we want x to be more than or exactly equal to 5 spaces away from 3 on a number line. So if we put 3 as the center on the number line, we're really imagining a circle of radius 5. And in that circle of radius 5, along the x-axis, we can either be exactly 5 spaces away to the left, moving negative 5 spaces, which takes us to a negative 2x coordinate, or 5 spaces to the right. I'm actually going to represent that as positive 5, and then the arrow carries the negative for the direction. Similarly, on the other side, we get to an x coordinate of 8. So our solution is going to be any x values that happen to be exactly 5 spaces away or more than 5 spaces away. So our solution will include the 8 as well as any point to the right. It will also include the negative 2 as well as any point to the left. And so our solution from a one-dimensional point of view is x is going to be less than or equal to negative 2 or x is greater than or equal to 8. From a two-dimensional point of view, we are going to look at solving graphically by drawing the graph in blue of y equals the absolute value of x minus 3. And let's say in red the graph of y equal to 5. And then the statement, the inequality we're solving, is comparing the height of the blue graph with the height of the red graph. And we want the blue graph and the red graph to intersect, as indicated by the equal to, or we want the blue graph to be higher than the red graph. So taking a look at the blue graph, we have the absolute value of x minus 3, which intersects here at 3. And so we know that the horizontal line of y equal to 5 intersects at y equal to 5 and is horizontal. And so we can take a look at the intersection points quite easily. Which may or may not be easy algebraically to work out, except we just did that. We found the intersection points to be negative 2 or 8. And then we also want the blue graph to be higher than the red graph. So we might imagine a line here that we can kind of scroll across. And as we scroll across, we're testing each x value. And looking up and down, we see that the blue graph right now is higher. And then at x equal to negative 2, the blue and the red graphs are equal in height. And then for the next interval, the red graph is going to be higher until we get to x equal 8, when they are equal in height again. And then after x equal to 8, the blue graph is purely higher. And so we can use that guide to help us to solve for the inequality, which is to say that we want the x values to be equal to negative 2, or to the left, or equal to 8, or to the right, which gives us the same solution as we found in the one-dimensional approach. Next, we want to determine the linear and quadratic approximations to this function at x equal to 0. We have some linearization and quadratic approximation formulas. I'm not going to focus on the quadratic one, but we will just go back to the linear one because this is nothing more than the equation of a tangent line. If you haven't seen the quadratic approximation, it's fine. It's coming up soon enough when we get to Taylor series. And here when we look at this, we see that L of x is nothing more than y. This f of a is the y-intercept. F prime of a is the m tangent, but we happen to know that for a linear function, m tangent is the same as m secant, which is regular old slope, rise over run. And then we have times x minus a. So this is a point slope form of the line. Now, I should actually clarify, this b is not necessarily the y-intercept because it depends on whether the a value, the x-coordinate that we're substituting in, is 0 or not. If a is equal to 0, then the corresponding y value is the y-intercept, and then we wouldn't have any x value here. It would just be x minus 0. So this is really the point-slope form of a line, which is the equation of the tangent line that we're looking for. So what we need to do first is determine the x-coordinate, the y-coordinate, and the tangent slope for the given x value. So we have 0, f of 0, and f prime of 0. So we know that f of 0 is going to be given by the function 1 over 1 minus 0, which is equal to 1, and we can work out the derivative. So this function f of x, I'm going to rewrite it as 1 minus x to the exponent negative 1, and so the derivative is going to be negative 1 minus x all to the negative 2 exponent multiplied by a negative 1 for the chain rule. And so we end up getting that the derivative is positive 1 over 1 minus x all squared, which is the same as x minus 1 all squared. And therefore f prime of 0 is going to be 1 over 0 minus 1 all squared is going to be 1. And so the linearization, or the tangent line equation, is going to give us y equals, well, let me put it in point-slope form. Y minus the y-coordinate is equal to the tangent slope times x minus the x-coordinate. Kind of a boring equation. So we get y equals x plus 1. And so if we wanted to write it in the linearization formula, y on the line is given by L of x, which is equal to, we can put the constant first, and then plus x. We'll see why this might be interesting later on, but for now it's fine to write the equation of the tangent line in familiar ways. The next part of the warm-up is to expand and evaluate or simplify the telescoped sum. So here we have this telescoped sum from I equals 1 to n of I plus 1 cubed minus I cubed. Now there's two characteristics of a telescoping sum. We have a subtraction in between, and we also have two consecutive input values, I plus 1 and I, or maybe it's I and I minus 1. And they don't have to be in bigger minus smaller order. It's just a matter that we have consecutive inputs and they are being subtracted according to the certain function. So if we use telescoping to expand this, it might be useful just to write a few terms out to see what happens. But obviously with an end boundary value of n, it's not possible to expand it completely because we don't know how many terms to go to. So we're going to get, the first time through I is equal to 1, we're going to get 2 cubed minus 1 cubed. And then we're going to add. The next time through I is equal to 2, we get 3 cubed minus 2 cubed, and maybe just one more. 4 cubed minus 3 cubed, and then plus dot dot dot. And then we move on maybe to the second to last term. And if you're not sure what that is yet, we could leave a gap and we could just fill in the last term, which we know is going to involve n. So we will have n plus 1 all cubed, and then minus n cubed. So the term before this is going to be I equals n minus 1. And so we have n minus 1 plus 1, which is going to be n cubed, and minus n minus 1 all cubed. So we see that some of the terms are written twice, except one version is positive and one version is negative. And that happens to be all of the interior terms. And the only ones that remain or survive the telescoping are the very beginning and the very end. And so we end up getting n plus 1 quantity all cubed minus 1 cubed, and we can simplify that further using Pascal's triangle if needed, or permutations and combinations if you happen to know that. And we can pick the appropriate row for the cubing function, which is going to be this one, and the coefficients for the n plus 1 cubed expansion will be 1, 3, 3, 1. And then we subtract the 1 at the end, and we have a cubic polynomial in n when we are finished.